In this section, we'll be looking at cathodic protection in concrete. We'll build a model using 2D, and we should produce results for the current density for hydrogen evolution, ion oxidation, oxygen reduction, and also make a plot of the oxygen concentration over a period of over different values of pore saturation. And also we should be able to make a plot of the electrolyte potential for a different range of pore saturation values. So we should come up with this results, and I hope you should be able to also produce this on your own after following this tutorial. If there are any questions, kindly drop them in the comment section, and I think we can get started. We start by going to our model wizard, where we select our space dimension. So we'll be dealing with the tertiary electroneutrality. We go to electrochemistry, tertiary current distribution. So we select this. That's the supporting electrolyte, and we add. Go on to steady, where we select stationary, which we go on to add. So this brings us to our Comsol interface, where we go to our parameters, which we'll be loading from file. So when we click to load our parameters, we'll be selecting the cathodic protection in concrete parameters. Alternatively, you could check it from your local DEX Comsol 5.5 or 5.4 multiphysics applications, Comsol model, then you find cathodic protection. So you go on to add the parameters. So we've been able to add our parameters to our work, from the Tafel slope to apply cell potential. Go on to definitions to add functions, interpolation. With our first interpolation, we want to add an interpolation from file, which is sigma. So the cathodic protection in concrete, sigma, is what we want to add. We go ahead to click to add, which loads our interpolation data, as you can see. Then we name our function sigma. The function units defined as m. So then we want to go ahead to plot it. As you can see, gives us the interpolation. The interpolation results as plotted on the graph in here. We want to add a second interpolation. So we'll load from file, which is the cathodic protection component D02. These are the values, as you see. We want to name the function name as D underscore 02. And the function unit should be M. 2s shown, then we go ahead to plot, have a plot of a function. Subsequently, we go ahead to build our geometry. We start with a rectangle. And since we already have our parameters defined, we have W, which is the width of concrete section. S is the concrete thickness. This R underscore bar is the reinforcing bar radius. So these are the parameters, or the the expressions for the parameters which we'll be using. So instead of me actually inputting the actual values, I would have to just input the name of the expression. So I'll just input W or S in here, which makes it easier for our work. So our width is W, our height is L, which is the thickness. The base should be at the corner. So we can build selected and get our quickly, if we've been able to build a simple rectangle. We'll continue by adding a circle. Circle, we want the radius to be, as you can see, R underscore V bar. The sector should be 360. Position should be S plus R. Sorry. R V bar. And Y should be L. Those selected, we have this. Now we want to make this circle cut through this rectangle. So the circle should cut through this rectangle so that we have a hollow semicircle in here. So how can we do this? If we want to make this circle cut this rectangle that we've actually built. We do this by going to Booleans partitions, where we introduce difference. So this difference will allow us to, we select R1, which is, so the object add is the R1. And so this R1 is the full rectangle. And the object we want to subtract from this rectangle is this, the circle one. That is what we want to subtract from it, so that we can have a semicircle shape formed here. So eventually we'll be able to build this. This is our geometry for our work. Geometry of our work that we'll be using. As you can see. We've been able to add our parameters, interpolation, and build our geometry. Now we go on to start modifying or adding certain electrode and electrode reactions to our work. So at the tertiary current distribution, you know that this section is the whole section, as you can see, one, defined with all the, is going to solve based on this equation, as you can see. Also solve it based on this equation. The electrolyte too as well. It's also this whole section. However, when we move to the diffusion coefficient, we select or we change this value to this PS, which should be isotropic. Charge number should be 0. The electrolyte conductivity should be user-defined. Sigma PS and isotropic. That's an electrolyte current conduction, which is this defined in here for us. Our flux go to insulation, go to initial values. Our initial values will define, before we define our initial values, we want to add electrode surface instead, before we define our initial values. So the first electrode surface that we'll add is this, where we go ahead to select, the section for our electrode surface. Look at our dissolving depositing species. Look at check our film resistance, check our boundary conditions. We also check potential based equilibrium potential as well. That's for the electrode potential. Go to the electrode reaction for the electrode potential, which we want to name as a zinc reaction, zinc oxidation, sorry. This section is a zinc oxidation. So since it's zinc oxidation, we'll be changing the equilibrium potential. We'll define it ourselves and we'll put it as this zinc. That is our electrode equilibrium potential. Our electrode potential kinetics should also be made as thermodynamic equilibrium. And our heat of reaction should be temperature derivative. These are defined. We go on to add another electrode surface too. So the electrode surface 2 will select this domain. That's 6 and 7 will be our domain. Move on to the external electric potential, which is E side. Perturbation amplitude 0 from 0, no from resistance. We have average of all reactions. So within this electrode surface reaction, there is an electrode reaction. This electrode reaction for the electrode surface 2 will be termed oxygen reduction. The oxygen reduction, number of participating electrons will be 4. Stoichiometric coefficients should be -1. The equilibrium potential should be user defined, where we select O2. The kinetics expression should be cathodic potential, where we have C let's go 0 O2. So I plus I0 O2. So we'll define C later on during our work, which will help us, which will later on make this whole expression known. So during the course of our work, we'll actually change this C to a particular section in the initial value. So that this exchange current density will actually be defined. For the benefit of, let me just change it for now. Let me just define what C will be. So we move to the initial values. So in the initial values, we make this C1, we want to choose C1. So we want to use C1. Actually, C1 will be C 0 to F. So that is the value for C1. So the same C1 is going to represent this. That's the concentration. And it's defined in here. So in order not to confuse or to make everyone understand it properly, I've actually defined, I've actually rectified the side to be C1. I've made the side C1 because at the initial values, our concentration that we're using is C1. We define it as this. That's the concentration of the oxygen over here, right here. Our cathodic cathode slope should be A O2, and temperature derivative user defined. Good. So we've been able to make all the changes in the oxygen reduction, the electrode reaction in the oxygen, made all the changes, necessary changes that we have to do. I'd like us to add another, we're going to add another electrode reaction to the electrode surface too. We're going to define this electrode reaction as the ion oxidation. Ion oxidation. That's our equation. The number of participating electrons is 1. We move on to the electrode potential, where we, as usual, we make a user defined in order to put our expressions in here. So electrode potential is defined in here. So all these expressions that we're putting all have been defined in our parameters over here. So that's for zinc, ion, hydrogen, everything is in here. So in case you're wondering why I'm putting these things, they're all in our parameters. Our kinetics, we want to use a anodic type of equation. We want to input our exchange current density as this. We want to input our anodic type of slope as this. Temperature derivative of equilibrium potential is user defined. We're able to modify our ion oxidation. And we go ahead to add another electrode reaction, which is the hydrogen evolution. So as usual, we come to our equilibrium potential, where we change this to user defined, and we put in this expression for hydrogen. Also, we change the electrode kinetics to cathodic Tafel equation. Change this to this, as you can see, and also we change the cathodic Tafel slope as well for hydrogen. All these expressions are defined in our parameters. All these are for our parameters. This as well is user defined. So you're able to make all these necessary changes for the hydrogen evolution. So after this, what we can go on to add is we can add a concentration. We add a concentration to our work. Sorry, concentration to our work. Our concentration should be here. The species, we choose species C1, which will define as C score O to score reference. That is it for our concentration. Make sure our electrolyte, everything has been defined properly. Our flags, check. First part is overridden. Isolation, first and sixth overridden. Initial values as well. We have defined what our concentration is. In our electrode reaction surface, identify the domain. Think oxidation. Define the equilibrium potential, where we input the expression, the value for it. Also the electrode kinetics, we made it thermodynamic equilibrium. When we move to the electrode surface 2, we actually selected the domain. Then we put the expression for the external electric potential. For the oxygen reduction, we put the exchange current density, cathodic Tafel slope expression, we're using cathodic Tafel equation. So that's this number of participating. Realize that for oxygen, we used 4 for oxygen. Iron as well. It's same, ensuring that all our expressions are been input correctly. So whilst I'm cross-checking, please kindly also check yours to ensure that everything is in order. You just have to double check concentration, which we've defined for 1. So once we've been able to double check all our equations and our expressions, we can go ahead to build our mesh. We want to select an extra fine element size, which we'll go ahead to build. So beautifully, we've been able to build this mesh, which is quite easy for anyone to do. We move to our stationary where we want to make some additions to our state. We want to add an auxiliary sweep to our work. So we select the pore saturation. It should be in the range of, let's say, 0.2. Want to loss of 0.5. Sorry. Results stored, steps stored in this, and also okay. So after doing this, I think we can go ahead to compute our work. So being able to compute our work, which took quite a very short time. So we see the electrolyte current density against potential, showing the potential intensity as we move away from this section towards the other side. So we have our some results that will actually check it out. So as you can see in here, we have been able to compute our results for our electrolyte potential and come up with how the electrolyte potential varies across the whole geometry. Also, we could see the electrolyte potential respect to ground, electrode potential versus adjacent reference as well. So let's go ahead to add a 1D plot group, which we want to name as the rebar potential. Adding a 1D plot group, which is, so this 1D plot group, we go ahead to add call a point graph. Point graph, we're going to select 3, 4, and 5. We want to find the rebar potential. And our expression, we want to put this CCD dot EVSRF. So it gives you the electric potential versus adjacent reference. Our title should be automatic. Let's make some changes in our legends. We want to show our legends and we want it to be manual. We want front. We want mid. Sorry, we want front. We want middle. We want black. Go ahead to plot, and as you can see, we have our electrode potential versus adjacent reference. As shown. You can go ahead to add another 1D plot group to show the oxygen concentration. Show the oxygen concentration. So we add a point graph for the oxygen concentration. We select 3, 4, 5, and once expression is C, unit is mole per cube. Which gives us the concentration. Move ahead to show legends. It should be manual. Want to set our own legends. Same as well. Want front, middle, and back. Okay, so this has to be, sorry, this has to be more. So actually, let me double check this section. We go to check our concentration. Oxygen, sorry, I think this is C1. Yeah, this C1 because in our oxygen reduction, the initial equation, we define this as C1 for the oxygen, concentration of oxygen. So when we are doing the oxygen concentration of being a point graph, we have to define the expression as C1. So as you can see, as we define it as C1, the plot has been generated over here. Concentration, oxygen concentration for the front, middle, and back section. We go ahead to add another 1D plot group, which we want to name as the oxygen reduction current density. We add a point graph to this. For our oxygen reduction current density, we add a point graph. The point graph will select this areas and we put this expression TCD dot IOC, which is the local current density. And our legends should be manual. We want to show for front, middle, and back. Wow, so we can see our local current density at the oxygen reduction. For front, you can see the current density is high, and at the, sorry, this is for front, current density very low. For at the back, have a higher current density compared to low, compared to the front. We want to also add another 1D plot group, which is the ion oxidation current density. So for the ion oxidation current density too as well, we go ahead to add point graph. We select this area, section 3, 4, and 5. And for the expression, we put this expression in there. Put this expression. That's for our local current density. Front is the middle. This is our back. Go ahead to plot, and we have a local current density at the ion oxidation section. For the ion oxidation current density, this is the plot of it. The local current density at the front, middle, and back. That's for the ion oxidation current density. And we want to add another 1D plot group, which will be the hydrogen evolution density. So the hydrogen evolution current density, the point graph. So go ahead to select this area 3, 4, and 5, and put our expression CB.ILO. So meaning that at the hydrogen evolution, the current density that we'll have for the front, middle, and back. This actually what you're seeing, front, middle, and back. So the current density at the front, middle, and back, if you should make a plot of it, you should have something. Let me name the legends before we can go on. For the front, middle, and back. This is how the plot should be. That's for the hydrogen evolution. Local current density at the back. This is the front. This is the back. So we can see difference in the current density for hydrogen evolution, that of the hydrogen ion oxidation. As you can see, that there's also a difference in the local current density for the ion oxidation. You can also see the local current density for the oxygen reduction in these graphs, as we've shown over for the front, middle, and back. And also we've seen the oxygen concentration for the front, middle, and back. So for the front, middle, and back, these are the concentration values shown over here. We've also seen the rebar potential for the front, middle, and back. And also we should remember that we actually looking at it for a range of pore saturation from 0.2 to 0.8. So the pore saturation, so the range of 0.2 to 0.8. So depending on the pore size, the pore saturation, this is the values of the electrode potentials versus the adjacent reference for the front, middle, and back over this range of pore saturation, as you can see. We can go on to, if you want to see that of the, for instance, if you want to see a different parameter, maybe for the rebar radius, maybe for the concrete thickness, depending on the type of parameter we want to actually study. We can do that. All we have to do is just change the parameter, change the range of values, then we'll be able to make a plot of all these, as you've seen over here. So this is the electrolyte potential over a range of these pore saturation, as we've shown over here. And the electrode potential versus adjacent reference, as we've shown over here. So this brings us to the end of our section, and thank you for following, and I hope you're able to build this model and you're able to understand what we just did. So if there are any questions, kindly drop them in the comment section, and kindly give this video a like as well. And if you haven't subscribed, please do well to subscribe. Thank you for watching.